Hello, everyone. Thank you so much for joining us today. We're going to be getting started with the webinar in just a couple of minutes here. But before we get started, I'd love to tell you about some upcoming events. On Wednesday, June 21st, we'll have the aspects of backpack vacuum use, evaluation of carriage location and sweeping technique with Huan Lin, PhD, CPE, and the Northwest Center for Occupational Health and Safety. On Wednesday, June 28th, we'll have Fired by an App, rideshare drivers' experience with discrimination, harassment, and unfair termination with the California Labor Lab. We'll be taking a brief break from our ERC Industrial Hygiene series in July and August, and we'll be back on September 12th, 2023 with the Southwest Center for Occupational and Environmental Health at the University of Texas. For more, you can visit us at coeh.berkeley.edu/about-CE. And without further ado, it is my pleasure to welcome you to the Industrial Hygiene webinar series. This is a collaborative effort on behalf of each Education and Research Center's continuing education program throughout the country, and it aspires to provide access to current research supported through NIOSH ERC programs. We appreciate you being here with us today. Today's webinar, Sampling Methods for Personal Exposure to Herbicides, is brought to you by Patrick O'Shaughnessy, PhD, CIH, FAIHA, and the Heartland Center for Occupational Health and Safety. The Heartland Center for Occupational Health and Safety has been in existence since 2000 and is proud of the academic programs they offer. They're always happy to take on new students and provide assistance to those in the OEHS world. Thank you for being here with us. A few more little housekeeping announcements. You are going to be muted during this presentation. If you'd like to ask a question, please enter it into the online Q&A, and we'll save time at the end of the presentation to address as many questions as possible. This presentation is being recorded and will be made available on the COEH YouTube page. And all participants who log in with their registration email for the full live presentation will receive an email tomorrow with a link to the evaluation form that will qualify participants for a certificate of completion worth 1 continuing education contact hour. Once the evaluation form is completed, you'll be able to access and print your certificate. And at this time, it's my pleasure to welcome our presenter today, Dr. Patrick O'Shaughnessy. Patrick O'Shaughnessy, PhD, CIH, FAIHA, joined the faculty at the University of Iowa in 1997, where he holds the rank Professor in the Department of Occupational and Environmental Health. He's a member of the Industrial Hygiene faculty in that department and is also director of the NIOSH ERC at the University of Iowa, the Heartland Center for Occupational Health and Safety. Dr. O'Shaughnessy is a recognized scholar in the field of aerosol physics, respirator performance, and human exposure assessment applied to occupational and environmental health concerns. Thank you so much for being here with us today and joining us to give this presentation. We're looking forward to it.
Okay, thanks. And thank you all for joining in. Boy, 1997, seems like it's been a while here. And over that time, engaged in a lot of different activities associated with industrial hygiene and some outdoor stuff as well. When the whole nanotechnology thing came along, I jumped on board there. And this activity, or the research I'm going to present here today, is kind of an offshoot of a variety of different things, all more or less related to aerosols in general, which is my expertise area. And so with that, I will pull up my screen here and get started. And I assume you can hear me and you can see a full screen that shows the title page.
Yes, we are all set. Thank you.
Okay, great. Thanks. So I'd like to start with acknowledgements, because if I don't, I'll forget them at the very end. I start with Mike Murphy. He's an industrial hygienist at 3M Corporation, who put this whole concept into my ear about 10 years ago, when I was wondering about pesticide sampling or sampling of other types of compounds that are volatile, as I'll explain, and this thing called its IFV notation. And so that's what's instigated all this, and many years later now have a variety of different research outputs from this that I'll discuss during this talk. I'd also like to acknowledge Ralph Altmeyer. He's a research scientist here at the University of Iowa and knows all things industrial hygiene when it comes to getting equipment up and running and that sort of thing, and it's instrumental for everything we've done here, literally. And funding, yes, from NIOSH, the Heartland Center for Occupational Health and Safety, supported the students that have worked on this project, and the NIEHS through, we have an Environmental Health Sciences Research Center that has helped with a lot of the equipment and other things in the lab space, et cetera. And I'd like to highlight the 3 students that have worked on this. Excuse me, I'm going to try to get rid of my floating panel. There we go. So Shauna Alex did a thesis project called Evaluating the Particle Phase Collection Efficiency of a Personal Pesticide Sampler. Got everything going for us. Matt Sobers compared sampling methods to detect airborne concentrations of semi-volatile organic compounds, which is, again, all related to what I'm going to talk about. And then most recently, Spencer Baker, also a master's student in industrial hygiene here, evaluated 2 of the pesticide samplers that I'll talk about in actual field settings of Iowa pesticide applicators. So I'm combining a lot of what they did, and including some of their thesis presentations and other work that they've shown at the Industrial Hygiene Conference. So to start off real generally, the pesticide industry itself is huge. When, of course, the term pesticide is kind of global, it can, from anything from an herbicide up to a rodenticide or fungicide. I'll refer to the term here as specifically to herbicides and insecticides applied to agricultural areas and or, of course, field settings, golf courses, and that sort of thing. Of course, it's all estimates, but somewhere upwards of 1 billion pounds of pesticides used in the US annually, which is incredible to think about. And there are somewhere in the neighborhood of 1 million pesticide applicators as well, from, again, folks that are doing it almost in-house to full-scale applicators out there in the fields of Iowa, for example. You can see here they're using a variety of different techniques to do that. And the spraying can occur, again, at the person level or utilizing a variety of different machinery. So it goes from a little pump sprayer I don't show here that you just hold in your hand, give it some pumps and get the pressure built up. Liquid goes out a nozzle, and of course the spray nozzle itself is specifically designed to eject a droplet of a certain size, primarily within a range, of course, but that the applicator can spot check around. And then it gets into more and more sophisticated application methods depending on the amount of area to be applied. So ATVs, rather smaller vehicles, can be retrofitted, as well as these utility task vehicles, UTVs, which are larger. And I'll show you some examples of that. You can see over on the right here is a typical UTV type of thing with this boom that's coming out in the front with the sprays coming down to cover, say, a football field or something like that. Used in maybe university settings. A lot of parks, recreational areas use that sort of device, keep dandelions down, etc. They can be riding or stand on. And then there's the large scale boom sprayers that we see here in Iowa and other places for agricultural and cropland. Here's like a 16-row applicator. Here, and I should have had a photo of one from Iowa specifically. Got these very large wheels or tires, so they can go above the growing corn, and with the wheels in between the rows, as shown here, and spraying out. When I came here in '97 from Vermont, I was just totally amazed seeing something like that coming down the road at me, which is high enough for a motorcyclist to drive underneath. So there's quite a bit of that in areas like the Corn Belt here. Now, of course, there's going to be exposures, and there's going to be health risks associated with those exposures to the variety of insecticides and herbicides. I'm kind of lumping them all together here on this slide. I don't want to get too far into this because it's a whole nother area of science in itself, which is the the health effects, where they come from, how they're derived, et cetera. But we can assume that, acute exposures to, say, especially a high hit, so to speak, of inhalation of an herbicide being sprayed can cause some airway inflammation, resulting coughing and wheezing, perhaps headaches, nausea. So both lung type conditions as well as central nervous system effects. And that's where, especially in the chronic level exposures, the CNS system effects come out with even upwards of increased risk of dementia, Alzheimer's disease, Parkinson's, and others, especially to the insecticides. And even current research here at Iowa is looking closer and closer at the herbicide issue as well in terms of their effects. So it's obvious need to protect workers. In this talk, I'm going to be focusing specifically on inhalation and the risks associated with that, and primarily the sampling methodologies associated with inhalation. And I will not discuss dermal exposures, which would be equally important for many pesticides as well. So the factors that might affect exposure, as you can imagine, associated with the application method. I already showed you a few different types from the personal sprayer up through the UTV operator, for example. So obviously there's going to be different aspects of the droplets and the vapors that are associated with them, associated with the application method itself. Of course, the higher that the wand here, for example, is being held for whatever reason, the closer it is to the breathing zone, the more risk is associated with it also. And then there's the obvious also is, is PPE being used or not used? And in this case, again, thinking of inhalation, more concerned with respirators of one type or another being utilized. Whereas you can see a worker here is wearing long sleeve shirts, a hat, a long sleeve, or pants, of course, closed toe shoes, those sorts of things to keep the droplets off their skin, which would be, again, back to the dermal problem. And then environmental factors. So this is all being done outdoors primarily. There's some insecticide spraying indoors, of course, for cockroaches and that sort of thing, but I'm going to focus more on the outdoor. And the biggie here in terms of the factor is wind, and what's its speed and what's its direction relative to the wand and when you're using it and the spray, as again, be somewhat obvious. Temperature, the higher the temperature, the more it's going to vaporize, and relative humidity can also affect the vaporization of the pesticide. And so that gets into this concept of the different phases of the pesticide, which I'll discuss even more as we go along here, because it's kind of critical that it obviously is sprayed out as a droplet, but it can also form a vapor. And then it's a matter of whether you have the droplet, the vapor, or both to be assessed when doing a proper exposure assessment of these applicators. So I need to go into a little bit of physics here now, so I hope you don't mind, to try to just kind of bring us all up to speed on, what is it we're dealing with in terms of the physical characteristics of most insecticides and many herbicides. And they can be thrown into this general category of semi-volatile organic compounds, SVOCs. So they have vapor pressures somewhere between 10 to the minus 7 and 10 to the minus 1 millimeters of mercury. In terms of atmospheres, you can just back it off one digit. So it's about 10 to the minus 8 to 10 to the minus 2 atmospheres. And boiling points between 240 to 400 degrees centigrade, so pretty high. So these are actually vapor pressures, I'll talk about them more too, that are pretty low, but the idea is that there's still evaporation that will occur in typical ambient temperatures. but you're not going to get some instant vaporization out of them. So they're not going to all just go foomph into a vapor form. So just for comparison, in terms of something that would really vaporize very fast would be liquid carbon dioxide. Right. So we know that it obviously exists exclusively as a gas actually in the atmosphere. And the reason here is you can see the vapor pressure is 4 times 10 to the 5th, not into the minuses, but into the 5th millimeters of mercury. So that means it's exerting this pressure against the atmosphere that's extremely high. And it basically just wants to kind of bust out of its liquid form into the gas form and will do so extremely quickly. Benzene, on the other hand, is 7 times 10 to the 2 millimeters of mercury. There's 760 millimeters of mercury for an atmosphere. So we're right at about that point right here. So benzene is right at that cusp of trying to get to the point of being a vapor rather quickly, but still will maintain itself as a liquid for a certain amount of time. And then water is at 2 times 10 to the 1st, so it's lower than an atmosphere. But you can see, interestingly, water has a vapor pressure that's higher than the SVOC. So it actually evaporates even faster. Just to give you a perspective on this for an SVOC. And here are some examples of these vapor pressures, again, in millimeters of mercury for some 2 different herbicides, allochlorin glyphosate, and then 3 insecticides, dieldrin, malathion, and chlorpyrifos. And you can see the ranges there, typically around 10 to the minus 5, all the way down to 10 to the minus 7 for glyphosate, which is going to be considered later in this conversation here. 4 of them, as you can see here, have a TLB, some have a PEL, some have a NIOSH REL. Glyphosate, interestingly enough, has neither of the above. If you're not familiar, that's the compound herbicide that goes into this trade name of Roundup, which is used heavily here in Iowa. They refer to Roundup Ready soybeans. So again, if you're not familiar and you live in Iowa long enough, you will learn all these agricultural tips and techniques. But so the soybean is genetically modified to resist the glyphosate. Whereas, of course, every weed around it gets killed by it. So you have to, if you want to grow soybean around here, you have to buy the Roundup Ready soybean because you know you're going to hit it with Roundup later on, and your soybean plants will survive, but the weeds will not. So that's the importance of glyphosate around here. Okay, so now again, we're kind of building up on this physical characteristics here a bit. And we could then start considering these spray conditions. So they're going to exist most likely as both a droplet and as a vapor. But again, this all depends on this vapor pressure issue. So the liquid, no matter what, is going to exit the sprayer as droplets. That's a guarantee. It's coming straight out of the liquid there. There's not enough time for it to instantly vaporize. So you're developing a droplet cloud, as you can see there. And then it's a matter of what's happening a little bit downwind or downstream. And you're going to have slowly evaporating droplets because they're SVOCs. And then, of course, there's going to be now this cloud, this vaporous cloud, due to the evaporated droplets. And so this therefore necessitates the need to develop some methodologies to get at the concentration of both the droplets and the vapor in order to have a total worker exposure concentration. And just to kind of drive this home a little bit more, I just kind of came up with this kind of cartoon looking thing. So, you know, as you're out there in that misty area beyond the sprayer, you're going to have a volume of air containing the vapor in the circle here, and pretending that this is kind of an expanding volume as it goes downwind, right? But it's getting more and more diluted as well. And then within it, you're going to have droplets of various sizes, depending on, you know, how they came out of the sprayer to begin with, and then their state because they are evaporating. So they are constantly shrinking. The And then, of course, the smaller the droplets, the more quickly they'll evaporate. So it's not a steady evaporation rate, but increases, accelerates as they get smaller and smaller. Why? Because there's more surface area per volume of smaller droplets. So it's a constantly changing state of nature, so to speak, that you're trying to assess as all this is changing in front of you, so to speak. And of course, affecting the worker in terms of is the initial droplet so large that they can't even inhale it, or are so small that before you even get them in, they have become vaporized. Now, to move this along a little bit further into the physics, I'd like to bring up this concept of the saturation vapor pressure first. So if you have a volatile liquid and you put it in a closed container, as shown here, say at a certain temperature, we'll go with 25 degrees centigrade, this head space will ultimately reach what's called a saturation vapor pressure. So the liquid is capable of evaporation under this temperature condition, and ultimately the molecules evaporating are equal to the molecules returning back to the liquid state itself. And so it becomes an equilibrium state at this certain pressure. So you can imagine that if you have a quote unquote a low saturation vapor pressure liquid at this certain temperature, you'll have lower pressure. And of course, a high liquid will result in this higher pressure. Now, in the world of industrial hygiene, we don't care so much about the pressure, we care about the concentration. So yes, there is such a thing as a saturation vapor concentration. So this will also result, obviously, we got these molecules are up in this headspace. And again, once this equilibrium develops and becomes stable, there is this saturation vapor concentration. Now, this and the saturation, I should go back and say, the saturation vapor pressure is, when I just talked about earlier, I talked about the vapor pressure. It's 10 to the minus fifth something. That is the saturation vapor pressure. It's the most it can possibly be. It's a way to enumerate it. Because obviously out in the atmosphere, it's going to be close to atmospheric pressure, and it will just keep exuding itself, trying to evaporate. Now we get to this concentration. This is the highest possible concentration of the vapor that can be exuded, so to speak, into an atmosphere. And now I'm using the same diagram, except I'm showing it at two different temperatures. So in this case, we have the same liquid, but obviously now if a lower temperature is going to have a lower concentration, and a higher temperature is going to have a higher concentration. So we have to consider this when we're measuring or the differences between a cold morning spray and a hot afternoon spray. Okay. So we're getting there slowly. Now we have to think about these concentrations relative to a threshold limit value, the ACGIH concept, right, of a threshold limit value, which is a concentration. So if the FVC, the saturation, which is the most it can possibly be, is much lower than the range of concentrations expected, which we hope is somewhere below the TLV, right? Then the pesticide is probably not one that is readily evaporating, and the sampler will capture mostly droplets because it's just not capable of a quick evaporation. And conversely, if the saturation vapor concentration is much higher than the range of concentrations expected, then the pesticide is readily evaporating and you're going to end up with mostly or only a vapor. So now your choices of a sampling device is, well, just collect the droplets on an absorbent filter of some sort and send them off to the lab for analysis. You don't need to worry about the vapor at all. If you have only vapor, well, you can sample with a sorbent tube and not worry about trying to collect the actual physical droplet itself. and have a really good understanding of, again, the exposure concentration to the worker. Now, at some point, I'm not sure the history, the folks at the ACGIH kind of tackled this issue of droplet versus vapor and came up with what they call an end note of inhalable fraction in vapor, IFV. So an IFV end note identifies a particular compound that has a TLV as being one that is probably going to exist in both phases, the liquid and the vapor. So you can see here are some examples. I put dieldrin, insecticide up on top here. Diesel fuel happens to be one as well, etc. They all have this IFE notation. I haven't added them all up, but there are dozens of compounds in the TLV book that are designated this way. So now this leads to the question of how did they decide to give this end note, and exactly what does it mean? So the concern, as far as I can figure it out, because I wasn't there at the time, is related to pesticides and these other SVOCs that I'm calling have a sweet spot. They have a sweet spot saturation vapor concentration. You know, it's not too high to be all vapor collected, and they're not too low to be all droplets collected. Therefore, you're collecting both vapor and droplet. So they enumerated it actually in terms of their choice as to whether this condition will occur by this utilization of a simple ratio of the saturation vapor concentration to the TLV concentration within these two orders of magnitude between 0.1 to 10. And so again, a really high SVC, as I just discussed, getting above 10, you're going to be mostly vapor, and below 0.1, you're going to be mostly droplets. So this is how the end note was designated to a particular compound type. So I'll go through a quick example here, the allichlor. Vapor pressure, as shown in the previous table, is 2.2 times 10 to the minus 5th millimeters of mercury. Has a molecular weight of 270. You can chug away at this equation here. And that 24.45 is the liters per mole, I think, at room temperature. And the rest is just to get all the units correct. And you end up with 0.32 milligrams per meter cubed as a saturation vapor concentration. And the TLV is 1 milligram per meter cubed. So just do the ratio here, 0.32 divided by 1, get 0.32. And therefore, the 0.32 is between the 0.1 to 10. Therefore, it's an IFV designated compound. So now from here on out, we're going to mostly talk about these sorts of compounds and how they're sampled. So again, given this IFE end note, the assumption is that two things have to happen. The concentration is of an inhalable fraction, that's what it's saying, the inhalable fraction of particles, and the vapor concentration must be measured. Well, for those of you who are in industrial hygiene, know that the word inhalable has a specific meaning. It is associated with what's called a sampling criterion of inhalable sized particles that can be inhaled into our respiratory system through the mouth. They are, in a sense, most easily thought of as all particles that can enter into our mouth and nose, upper airways, and go from there. So this suggests, by using the term inhalable fraction, suggests that an inhalable size selective sampler should be used to accurately assess droplet inhalation. Now, I'm saying all this assumption and suggesting because here is the actual wording in the TLV book. I won't go through it all, but it doesn't say anything like, and therefore thou shalt use an inhalable size selective sampler. So that's why it's an assumption at this point, and we have to work from there. Okay, so if that's true, then here is the size selective sampling or efficiency curve for the three basic types of sampling criterion established by folks back in the day, including the ACGIH, ISO, and others. And so, oops, sorry. The inhalable curve, as you can see here, and this is on a log scale down below, mind you, you can see it goes out to about a 50% efficiency at 100 microns. So this is suggesting that 100 micron particles, about 50% of them will enter our mouth. The other 50% just don't get in there. And above that, it drops off quickly. They're basically falling past our face because they're so heavy at that point, and we're not sucking them in. But it goes up, as you can see, rather quickly to 100% efficiency for the very small particles. So the point here then is to have a sampling device that mimics this curve when sampling for IFV noted and noted particles, pesticides. And one such sampler that can do this for dry particles is an IOM. It's called the Institute of Medicine. It's actually out of Britain, where this was developed, not an American Institute of Medicine. Inhalable sampler. So you can see it has a big hole in it, so it's facing outward. It's literally mimicking your mouth when you're kind of got it in a round circular shape of your lips. Now, this again gets back to the droplet size, and you can see here, according to some evidence, that spray applicators can get to about 4 to 15 microns. The boom sprayers are larger droplets, 25 to 500, but again, it makes sense that we'd be using the inhalable curve and trying to capture even larger diameter droplets as we can, because they do exist from these application methods. So now we get into the methods themselves. Again, we're trying to isolate out these sampling devices, and a classic one for organophosphorus pesticides, NIOSH method 5600. You see down here at the bottom left, the sampler is specifically stated. I'll blow it up for you here. It talks about a filter / solid sorbent tube, OVS-2 tube. Has a 13 millimeter quartz filter with XAD2 sorbent media in two different stages at 270 milligrams, 140 milligrams. So now it's like, what is this OVS-2? Well, first of all, the -2 stands for the XAD-2, which again is the type of sorbent media. So now we're down to the OVS, and it stands for the OSHA Versatile Sampler. So this thing was designed to measure aerosols and vapors simultaneously, which is exactly what we want. It's required by a variety of OSHA and NIOSH sampling methods, and it has one unfortunate characteristic, which is it is not and was not designed as a size selective sampler. So we can't assume that it is inhalable. When actually used, it's encased in a cowl, plastic cowl like this, and worn up near the lapel to capture both the vapors and the droplets. So then you see it points downward. So there's issues there in terms of pulling in an inhalable type of particle. So is there an IFV sampler? If there is, it has to have a size selective inlet to sample relative to the inhalable criterion, and it should have the capability of capturing the vapor phase compounds. And it just so happens that several years ago, SKC developed a sampler for that purpose. They call it the IFV Pro. It has an IOM-like sampling head, 25 millimeter cassette inside it. So you can see this shape up here is very similar to the IOM I just showed you earlier. And of course, then as air goes through, hits the filter first, and it comes down into a sorbent tube. And it's all encased into a plastic cowl like this as well. It's longer than the OVS. The OVS is about 4 inches long. This is about 8 inches long. And this head on it, you can see down below, is smaller, has a smaller diameter than the IOM. It's about a 10.6 millimeter inlet. It's operated at 1 liter per minute and gives you a face velocity of 18.8 centimeters per second, whereas the IOM is 15 millimeter inlet. It's operated at 2 liters per minute, but still gives you that 18.8. So that's the scaling that went on in order to have the same entry velocity, which is critical for having an inhalable sampler be what it is. Why the 1 liter per minute for the IFE? That's because of the constraint on the adsorbent tube, which you are not supposed to sample with a flow rate higher than 1 liter per minute. So that's the maximum. There are other sampling devices out there, two being developed in Europe, the German GTP device. You can see they use this sampling orifice, which is their equivalent of the IOM, followed by an adsorption tube. And they have a GTP mini, it's called, which is down at 0.5 liters per minute with a really interesting sampling head on the top end that, again, mimics the inhalable curve. So there are at least one other device out there. So now the experimental question is, what is the particle droplet collection efficiency of the OBS? Is it anything near an inhalable? And what is the collection efficiency of the IFE Pro? It wasn't previously validated. And how do their measurements of herbicide exposures compare? So that's where students came in to answer some of these questions. So I'll go through this briefly. In terms of the OVS aspiration efficiency, we compared the OVS to a 25 millimeter cassette pointing straight up in this vertical flow chamber that I'll show you to serve as an isokinetic sampler. So that's measuring the truth, the cassette. And meanwhile, we also had an IOM sampler in there as well. And the setup, we had a chamber, is basically just used as a containment vessel, within which we put 8-inch column ductwork with a honeycomb to straighten the flow straight down onto the samplers themselves, while we put in this graded inorganic dust with a known median diameter, which is a classic way of getting at these sampling curves. And you can see here we had the devices on a PVC pipe. Now here it's showing the OVS tube horizontal. We tried different configurations, but normally it would have been straight up and down with this opening on the downward side. And then in terms of data analysis, again, we compare the ratio of the OVS to the cassette, and then compare the OVS directly to the IOM as well. So here's just looking at the IOM, not the OVS, but just the IOM. This is kind of a check on our system. Does it work the way we expect it to? And there's this calm air curve that these points are following fairly well. So we felt pretty comfortable that our system is working the way it's supposed to. The IOM efficiency is following that calm air curve developed by others. But you can see now when we apply our data from the OVS, see a really drastic drop off. So it's not collecting anywhere near like an inhalable sampler should. And then looking at it simply from the point of a ratio of the OVS to IOM, and I see I have this wrong. This is not efficiency. This should be the ratio of the OVS to IOM. The average was around 34%. So the OVS is bringing in around a third of the mass of the IOM. It's one way to look at it. So that kind of explains and answers the questions about the OVS. Now for the IFV, we moved our labs and developed a more sophisticated vertical flow chamber where dust was put in up on top and came down through. And yes, we'd use dust because we're just caring about its collection characteristics of any particle, of which a droplet is one of them. And you can see here we have the SKC and the IOM all put together in the middle with the isokinetic sampler in the middle. And now in this case, for this particular chamber, the measurements followed this IOM efficiency curve much better. I don't have a good explanation for that, but the point is more how does the IFE follow that of the IOM. And you can see here really closely. And again, looking at this ratio, the IFE actually oversampled slightly, about 10%, 9% here is shown here, relative to the IOM, but certainly within reason and certainly not statistically different from the IOM. So it passed that test. So then in a secondary experiment, we decided to expose both of them to a dual phase aerosol, both droplet and vapor. And we chose ethylene glycol to do that because it has a vapor pressure that's pretty close to that of pesticides, and it's handled, cheap and safe and that sort of thing to spray in a lab. So we put in a big drum here. We used a spray bottle to eject it, and we had the samplers inside. As you can see here, we sprayed kind of away from them, but to develop the droplet and the vapor as well while they were sampling. And this is the results. It's a little messy, although colorful. You can see the green line and the purple line were the two cases where the OVS sampled higher than the IFV. But in all other cases, the OVS undersampled relative to the IFV Pro, which again was the expected result, to the point of about almost twice as high for the IFV Pro. So again, if this sort of suggests, of course, that use of the OVS may be underrepresenting the exposure if we're considering and concerned about all droplets of all sizes up to about 100 microns that are being inhaled. Now, wrapping up here, I'll talk about experiment 3. This is where Spencer took over recently, looking at herbicide sprayers themselves. He was able to find 6 participants from 3 different companies. Companies is used loosely here. Some of them were kind of governmental organizations and that sort of thing. It's very difficult to find independent operators willing to participate, as you can imagine. But subjects were sampled using both the OVS and the IFV Pro. And as it turned out, despite 3 different companies, they all used either glyphosate, again, the Roundup, or this herbicide called Horsepower, which has called MCPA and dicampa in it. And then he also had a survey of the workers. So you can see here we are in eastern central Iowa. So Spencer developed this system here of putting both samplers side by side. He's able to connect them to pumps in a backpack scenario like this, which the workers seem to appreciate, getting it out of the way of their hips. It was a little easier because 2 pumps had to be put in there at the same time, get that going. And he would rotate locations as well, left to right. They did a variety of different spraying though. So it wasn't just individuals with a spray wand, but they had this, they were riding this thing called a Z-Spray stand-on sprayer. You can see that the spray is actually in front of the driver in this case. Wouldn't be my favorite design, but that's the way it is. They were also sampled while mixing an herbicide from the concentrated solution. And here's on the left is more of a UTV, a Toro Multi-Pro turf sprayer. And you can see this is a pretty big boom on the backside. I don't know, it's 10 or 12 feet long. And another Z-Spray stand-on sprayer over to the right. And company C, they just happened to be engaged in trying to kick back some weeds growing on fence lines. So they were doing some spraying up higher, as you can see there. They retrofitted a Gravely mower with a platform to carry a big tank of the pesticide, so that they could just use a wand from there. And this guy would just follow along with the sprayer, so he didn't have to carry a big tank on his back. And with that, the results were all negative, as it turned out. They're all below the limit of quantification anyway. So that was something of a surprise, especially with the workers that were spraying, up sort of high on that fence line. So they had the one subject actually who was working with the horsepower, and the others that were working with glyphosate. You can see different LOQs, and much lower for the horsepower related compounds than for the glyphosate. And then Spencer just did the calculations knowing the sample flow rate and the sample time and the LOQ. He converted it to a maximum exposure concentration based on the LOQ, or the reporting limit. You can see it was very low for the horsepower and varied between about 0.4 to 1 for the glyphosate as a maximum possible concentration. Only dicampa has a PEL of 5 milligrams per meter cubed, so obviously way below that. In terms of his survey results, he asked them, how often do you spray? A monthly basis. Of course, that's during the spray seasons of basically fall and spring, and some in the summer. Received formal training. Yes, that was encouraging. Most of them used PPE of some sort. Again, they were worried about dermal exposures, primarily long sleeve pants, shirt, closed toe shoes, chemical resistant gloves, safety glasses. And then here's the interesting one. Every one of them considered the wind while spraying. So they did the obvious, which is, you can see the spray being moved by the wind, and they just made sure that their bodies were always upwind of the spray as it started moving relative to the wind as it pushed it along. So that obviously was very effective, as our results indicate, in terms of minimizing their exposures to the herbicides they were spraying. So the conclusion to that part of things was subjects were not exposed to significant levels. The current exposure reduction strategies they used were effective. They used proper PPE, they sprayed under ideal environmental conditions, and they restricted their spray time. And the lack of the pesticide collected by the samplers made a comprehensive sampler comparison infeasible. In other words, we were trying to do a side-by-side, but that didn't work out because of the non-detects through both instruments. So I'll just wrap up now. I'm at 2:47 minutes, and just a few considerations. There's some concern with the IFE Pro in terms of, the vapor part is getting beyond the filter up top, and then there's additional plumbing, so to speak, and a connector before you get to the sorbent tube. And so are there some losses there that may be relevant is one issue. And then in terms of its use, I don't know if anybody else has, but we've done it now 3 or 4 times in terms of sending off material to the lab, because we don't have that instrumentation here. So, the industrial hygienist needs to select the proper filter and the sorbent tube. You need to work with the lab to make sure that you are doing the correct sampling methodology with the correct type of OVS tube, for example, relative to the analysis method. Now, thankfully, most of them use either glass or quartz fiber filters. OSHA likes glass, NIOSH likes quartz. And most typically an XAD2 sorbent tube. So that keeps it simple there. And then, of course, you have this cassette here. You have to send that off with a filter in it. They provide you with this little container. But the first time we did that, we all of a sudden realized a month later, hey, where are our cassettes? And realized the lab didn't send them back. Well, so you have to ask them to send them back because they are worth money. So that's a little different than the OVS tube where they just toss that little glass tube into the trash. And then, you need to work up front with the lab before you even start everything. Make sure they know that they're going to be using a non-standard sampler if you're going to use the IFE Pro, because you have these 2 separate media that are distinctly separate versus them all kind of crammed together in the OVS tube. And you could have them desorbed together or separately. So that was one nice thing if you want to know what's on the filter versus what's in the sorbent tube, but you're going to pay double for that. And then there's this issue of, you're going to wash out the inside of the cassette. And we did not do that. We just asked them to analyze the filter and pull it out. There's a variety of different analytical methods, as you can see here from NIOSH and OSHA. And of these, you can see those that require the use of the OVS tube I'm highlighting here. So interestingly, we used 5001 for the dicampa, and MCPA didn't need an OVS tube. Here's at the bottom, the glyphosate didn't need an OVS tube. So both of those have a vapor pressure high enough or low enough that they really don't have to worry about the vapor phase. So I hate to just throw all that tube at the very end, but we really didn't think it through until, it became obvious towards the end of it, like, oh yeah, the vapor pressures are so low that as it shows here for glyphosate, you only need the method only requires a Gelman filter, does not require the use of a sorbent tube. And then for the dicampa, again, only requires a glass fiber filter. So that was an eye opener to us, thinking, oh, well, it's a herbicide, so therefore it must be something that we have to worry about, both vapor and droplets, but not necessarily according to the methods. So overall, the OVS sampler, according to our lab experiments and those conditions, within those conditions, undersampled relative to the inhalable convention, and the IFE Pro slightly oversampled, but certainly not statistically. And a survey of herbicide sprayers demonstrated very low exposure potential under the conditions sampled. And again, this warning that the industrial hygienist needs to be fully aware of the pesticide being sampled in the proper sampling method, work with the lab at the outset. And I don't want to put another plug for SKC, but they have this really nice sampling guide. Maybe I can pull that up. Oh, no, you can't see that. So that's something to access first. It'll tell you, for a particular compound, what method is most likely going to be used by a lab. And with that, I will stop the talk and thank you for your attention. And I'll be glad to discuss or answer any questions you may have.
Excellent. Thank you so much. I do see some questions now coming through in the chat and the Q&A here. First, does a sorbent tube collect both droplets and vapor?
The sorbent, well, the OVS, because it has a filter prior to the sorbent media, does collect both. But a classic sorbent tube where you crack one end open only contains sorbent media. So it will pull in a droplet, I guess, but it's not meant to do that specifically. It's only meant to sample vapors.
Thank you. Were you able to note any effects of temperature and humidity when collecting these air samples?
That's a good question. We did take temperature and relative humidity measurements, but we didn't correlate that back with measurements. Again, we had so many non-detects, so in terms of the outdoor measurements, that we couldn't tease out those environmental conditions. But certainly something as an industrial hygienist to bring along a temperature and relative humidity probe with you to make sure you have that as kind of backup information.
Thank you. We also had a question about environment. Would a different environment provide for a better comparison? For example, an enclosed greenhouse?
Yes. Yeah, I didn't talk about some of Spencer's additional work, which was trying to get at that point. It's a really good one. In terms of trying to come up with a confined space, say, that might give you a better control over temperature and relative humidity and how these vapors are doing their thing. So we actually created this tent that we worked in, but the one maybe design flaw was to put a fan in it to try to kind of kick up the aerosol that we were spraying. And actually his results showed that in doing that, I guess I had everything kind of roiled around in there a bit too much. whatever, both the OVS and the IFV sampled very similarly under that condition. But I would agree something as large as a greenhouse would be ideal, but we didn't get to that extent.
Thank you. Also kind of on the application scenarios, another question relating to if there was any differences noted by the type of spraying method, for example, handheld versus backpack versus using the vehicle.
Mm-hmm. Yeah, again, these were points that we were hoping we could distinguish from, because yeah, they did, that was ideal in terms of our selection of volunteers, that they were doing different things on using different methodologies. But again, we just couldn't tease it out because of the non-detects we got back. We were, again, the surprises were that we didn't notice a higher amount from the worker who was spraying up near his head height. And we were also expecting a higher amount from the use of the UTV that has the boom in front of the worker. So we were hoping to get at that a little bit better, but it didn't show up. So we've got to work on that one. Mm-hmm.
Thank you. I also want to circle to, personal protective equipment, and you mentioned dermal exposures as well. We have a question related to the IVF TLV for Daldrin and others has a skin notation. Would dermal sampling be of use to augment a study such as this? They're not sure if there's a correlation between skin exposure and what would be found by an IVF or OVS sampler.
Yeah, I gotta hire some of you folks to come into the lab here and help me out, because that's another great study. Again, we were focused on this IFV notation, which again, it has everything to do with the droplet, the aerosol phase, and did not get into dermal exposures. But yeah, obviously many of these types of compounds are also have the skin notation as well. So that would be another good follow-on study, I'll have to admit, in terms of trying to correlate those two and determining, what really is the greater hazard, right? Maybe what we've decided here is that the inhalation hazard in an outdoor environment, again, under the conditions that we sampled, surprisingly low amounts. And so maybe the greater hazard would have been to dermal in this case. So yeah, another great idea.
I was also personally surprised to not see masking as one of the PPE typically worn, that it really was oriented around those dermal exposures. And I'm just curious, based on your findings, do you consider that adequate? Would you still recommend a masking, or just your thoughts on that?
If I were doing it professionally year after year, I would definitely be masking up myself. I understand how uncomfortable, how just miserable it is, and many of us know now, thanks to COVID, forcing us into the situation of perhaps wearing an N95 for more than 30 minutes even, that it is not ideal at all. But I wouldn't feel comfortable until proven otherwise that I'm not inhaling more than I should. And we see this all the time, especially with at least I do, with the residential applicators in my neighborhood, for example, that are going around and you just smell the trail that they're leaving behind themselves. So they're certainly getting a vapor, guaranteed, and whether or not they're also getting a droplet is possible. So I think especially in those conditions, now the operators we did worked on, it's not their full-time job. Spraying is typically done sporadically in most cases, whereas the residential folks or those that do inside insecticide spraying to get rid of critters around houses and businesses, they're doing that constantly, and I think their PPE should be as high as possible. Mm-hmm.
Yeah. Another question, kind of noting to the use of this type of sampling method for other exposures and other substances, for example, spray painting. Do you think that would be a worthwhile application of this kind of information?
Yes, it would. Yep. Yeah, spray painting is a great example. We are definitely going to get the droplet and the vapor going on at the same time. And, to some extent, that in terms of PPE, there are the half mask and full face mask with the cartridges that will take care of both of those phases for you. There's the particulate filter followed by the activated carbon. So at least that type of PPE is available. But in terms of exposure assessment, yeah, that's actually a good idea in terms of combining these types of samplers to get at both phases.
Thank you so much. Thank you everyone who joined us today for all of your excellent questions. I know there were a few I didn't get to, so sorry about that, but hopefully you got some great information from the presentation. I do want to close with just this final question. What exactly do you recommend if someone were to go out and measure pesticide exposures, given all of the different options that you've shared with us today?
Mm-hmm. Yeah, well, the standard method in most cases requires the OBS. Therefore, you have to use that. The IFE Pro, however, would be a really good option to get at what would most likely be the real total exposure by way of inhalation because of its capabilities of getting at the larger droplets. So, yeah. Okay.
Excellent. Well, thank you so much again for this excellent presentation. I think hopefully you can see the reactions coming through. We've got some thumbs up, some smiley faces
nice.
and waves. So thank you so much for joining us today, Dr. O'Shaughnessy. Thank you for everybody who joined us and asked your excellent questions for today's webinar. As a reminder, this was recorded and you'll all be getting a link to the recording tomorrow at noon Pacific time. Thank you so much for all being here today. We appreciate you.
Thanks all. Bye-bye.
Bye-bye.